Welcome to the Olympic decathlon of your academic career, the Cambridge Physics Exam Strategy Masterclass. Think about it for a second. You have multiple, highly specific disciplines to master. You have incredibly complex challenges to overcome. And the clock? Well, the clock is always ticking. Now let's dive right into this explainer, because today we are tackling one of the absolute most foundational events in this entire decathlon, the kinetic particle model for IGCSE Physics, specifically focusing on syllabus code 0625. I really want you to picture the exam hall right now. You're sitting there. The invigilator at the front starts the timer. You flip open your paper and boom! Staring right back at you is a massive 6-mark question on particle structures and temperature relationships. Now I want to introduce you to two very different candidates sitting in that exact same room with you. We'll call them Alex and Sam. When Alex sees this question, pure panic sets in. Alex immediately overloads the page with raw physics facts, literally just dumping every single piece of trivia they have ever memorized onto the lines, completely lacking any sort of structural analysis. Then, on the other side of the room, there's Sam. Sam rushes. Sam is practically skimming the text and entirely misses the crucial, specific command words hidden within the question prompt. Throughout this strategy session, we are going to look closely at their fundamentally flawed answers, complete with the harsh reality of the examiner's red pen marks. And by the end of our time together, you are going to learn exactly how to transform your approach so you never make their mistakes. You're getting the ultimate insider's guide to thinking exactly like a Cambridge examiner.
15. I really want that number to sink in for a moment. Why on earth are we dedicating an entire comprehensive strategy session to just the kinetic particle model? Well, because this single topic, which encompasses the structure of solids, liquids, and gases, those tricky particle diagrams, the intricate relationship between microscopic motion and macroscopic temperature, and the concept of absolute zero, accounts for approximately 15% of the total marks in your 0625 physics examination. 15%? Let me be perfectly clear, that is not just some minor throwaway topic. That 15% is literally the difference between sitting on a B grade and securing an A star. It is an absolute powerhouse of a subject area, and, more importantly, it bleeds directly into other major topics like thermodynamics, gas laws, and energy transfer. If you don't confidently secure these baseline marks, you are essentially starting the race with a massive, heavy handicap. But if you master this, you build an unshakable, rock-solid foundation for the rest of your entire paper.
So how exactly do we conquer this beast of a topic? We need a highly structured roadmap to drastically lower your cognitive load. Here is the agenda for our masterclass. First, core principles. Second, absolute zero. Third, the method mark strategy. Fourth, our deconstruct, solve, and evaluate framework. And finally, number 5, examiner warnings. 10 disciplines, 10 challenges across this syllabus. And today, we master this one completely. Let's move. Okay, Section 1. Let's dive straight into our first major discipline, the core particle model principles. You cannot just guess your way through this.
Whenever you are asked to compare solids, liquids, and gases on the exam, examiners are waiting, pen in hand, expecting you to evaluate them strictly across 3 specific, syllabus-required dimensions. Those dimensions are arrangement, separation, and motion. Remember our friend Alex? Alex would just write a messy paragraph saying something like, solids are hard, liquids pour easily, and gases kind of float around. That gets exactly 0 marks for analytical depth. A Cambridge examiner expects you to categorize scientifically. Let's break it down. For a solid, the arrangement is a regular, repeating lattice. The separation is that particles are touching with minimal space between them. And the motion? It is strictly vibrating about fixed positions. Now for a liquid, the arrangement is random. The separation is slightly further apart, but they are mostly still touching, and the motion is sliding or flowing past one another. Finally, for a gas, the arrangement is completely random. The separation is vast compared to the actual size of the particles, and the motion is rapid and random in all directions. You absolutely must use these precise terms. If you don't specifically hit arrangement, separation, and motion, you are literally leaving easy marks on the table. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Let me tell you a secret. Rote memorization will entirely fail you when Cambridge throws a weird curveball context at you under pressure. Instead, you need to use what we call the visual story method to encode these complex particle diagrams into your long-term memory. Imagine a packed stadium for a solid. Everyone is in their officially assigned seat, shoulder to shoulder, just vibrating with excitement but completely unable to actually get up and move around. Then, the concert ends and people start flowing out into the crowded hallways. That is your liquid state, still very crowded but randomly sliding past each other. Finally, they hit the massive empty parking lot and sprint to their individual cars in every possible direction. That's your gas. When you create a vivid visual narrative like this, your brain retrieves the data instantly. This frees up your mental energy, allowing you to focus on structuring your answer rather than struggling to recall basic facts.
Moving seamlessly from those states of matter, we arrive at Section 2, the critical anchor concept of extreme temperature limits, defining absolute zero.
You see, temperature is not just some random number on a thermometer. In physics, it is a direct measurement of average kinetic energy. And to truly understand kinetic energy, we have to look at what happens when it completely disappears. The crucial point here is this highly specific definition, absolute zero. It is exactly negative 273 degrees Celsius. Please, whatever you do, do not just write it gets really cold. Absolute zero is the theoretical temperature limit where all particle motion completely ceases. The kinetic energy literally drops to zero. Our panicked friend Alex lost a massive mark here in a recent past paper because he wrote, "The particles freeze." No, particles in a solid are already frozen into a lattice structure, but they are still vibrating, right? At absolute zero, even that microscopic vibration stops entirely. This is the absolute bedrock of the relationship between particle motion and temperature. As temperature increases, kinetic energy increases, and velocity increases. At absolute zero, that entire relationship ceases because motion is fundamentally eliminated.
All right, Section 3. Now we are shifting gears from theoretical physics facts to actual technical execution. This is where the decathlon gets seriously intense. Let's look at the method mark strategy.
Knowing the physics is honestly only half the battle. Knowing exactly how to communicate it to a Cambridge examiner is the other half. I want you to read this quote directly from the official principal examiner reports. The assessment framework prioritizes analytical depth over superficial breadth. This right here is exactly why Sam fails. Sam rushes and provides a superficial, surface-level answer. When the command word on the paper is explain, you cannot just state a bunch of facts. You have to dive deep. This is where the absolute top-tier students use the Peel framework. Point, evidence, explanation, link. Let me break that down. Your point states the direct physics fact. Your evidence provides the specific data or syllabus principle. Your explanation details the exact why and how, and your link connects it right back to the highly specific scenario presented in the question prompt. If the command word is describe, they just want the what, but if it's explain, they demand the why. The examiners are literally handing you a treasure map to the marks. You just have to follow the Peel structure to dig them up.
Moving into Section 4. To consistently apply that Peel framework and hit those command words perfectly under severe exam pressure, you need a systematic sequence. But hey, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @theexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's get back into our framework. Deconstruct, solve, and evaluate.
I want you to imagine a 60-second timer ticking down on your screen right now. We are officially entering our interactive workshop phase, and we need to move fast. Challenge 1 is the data scan. Here is your systematic 3-step framework for any complex problem. Step 1. Deconstruct the question and extract the data. When you see a complex physics chart or a massive, dense paragraph about a gas expanding in a cylinder, you don't just passively read it, you actively mine it. Extract the temperatures, pull out the volumes, and critically, underline the command word. Step 2. Solve systematically by applying relevant principles. This is where you deploy your Peel framework. Bring in the kinetic particle model facts we just covered. Step 3. Evaluate your results for reasonableness. This is your time management matrix check. Take a step back and look at your final answer. Does it make logical real-world physics sense? If you calculate that a gas cooled by 10 degrees suddenly gained a massive amount of kinetic energy, your evaluation step should be triggering huge alarm bells in your head. Deconstruct, solve, evaluate. This 3-step rhythm is exactly how the red ink of Alex and Sam transforms into the green check marks of an A-star student.
Now for an insider tip. The defining difference between an average candidate and a truly elite candidate comes down to one thing: causal chains. Examiners wildly reward precise causal relationships and cross-topic connections. It is simply not enough to write, "the gas gets hot and expands." You need to provide the entire causal chain. Here's how it sounds. Increased thermal energy transfers to increased kinetic energy of the gas molecules. This leads to higher velocity particles, resulting in more frequent and more forceful collisions with the internal walls of the container, which therefore increases the internal pressure, ultimately causing volume expansion. Boom! That is what we mean by analytical depth. Furthermore, when you connect the kinetic particle model to things like specific heat capacity or pressure laws from totally different syllabus sections, it proves to the examiner that you don't just blindly memorize isolated facts, you actually understand physics as one unified interconnected system.
Section 5. Even with the absolute best frameworks, under the crushing pressure of the exam timer, mistakes happen. So let's look at the dark side of the decathlon and address the top examiner warnings.
We have thoroughly scanned the principal examiner reports to uncover exactly where thousands of students are consistently hemorrhaging marks on this specific 0625 topic. It's time for Challenge 2, the Find the Flaw Challenge. Here are the top 3 fatal errors. Number 1. Answers are way too vague and lack specific details. Writing something like, particles move faster when it gets hot, is a middle school level answer. You must upgrade your vocabulary and say, the average kinetic energy of the molecules increases. Number 2. Format, correct terminology, and presentation conventions are completely ignored. We see students drawing particle diagrams where gas particles are the size of tennis balls or liquid particles aren't even touching each other. Precision absolutely matters here. And number 3, honestly, this is the biggest one, explanations are not specific to the provided context. If the exam question is about a specific experiment involving a balloon and a freezer, and you just write out the dictionary definition of absolute zero without ever once mentioning the balloon, you are going to lose all the application marks. Sam does this constantly, rushing past the real-world scenario to just dump a memorized textbook definition.
Let's lock this concept in with a direct comparison. This is Challenge 3, a speed writing challenge. Imagine you have a 30-second timer counting down right now to write one perfect Peel paragraph. The exam question asks, explain why a seal deodorant can explode if it's thrown into a fire. The classic mistake, our friend Alex's typical approach, is providing a generic, memorized definition. Alex writes, gases expand when heated because the particles move more. Zero context, zero analytical depth. Now, look at the examiner's standard. This is about linking every single specific detail directly to the unique context of the question. An A-star Peel response reads like this. As the thermal energy from the fire transfers to the gas inside the sealed can, the average kinetic energy of the gas molecules drastically increases. This causes the gas molecules to collide with the internal walls of the metal can much more frequently and with significantly greater force. Because the volume of the can is fixed, this immense increase in internal pressure eventually exceeds the structural integrity of the metal, causing the resulting explosion. Do you see the massive difference there? It is highly precise, it utilizes the correct scientific terminology, and it is entirely married to the specific context of the can and the fire.
So, we have finally arrived at the finish line of this specific event. We've gone from a 0% mark potential right up to 100%. The complete physics answering system comes down to 3 non-negotiable rules that guarantee top marks. Number 1, command word decoding. Number 2, strict Peel framework application. And number 3, using your time management matrix to evaluate your answers. Students who implement these exact physics strategies see an average improvement of 2 full grade boundaries, but that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @AceTheExams_IGCE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCE and click that bell. Don't let another exam pass you by. Before you go, drop a comment below with your target grade for physics and the absolute biggest challenge you're currently facing. Our team responds to every single comment. Make sure to like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. When you encounter your next particle diagram, what will you do? The choice and the grade is entirely yours.